The sun is not eternal, it is a ticking clock, and someday our time runs out. Stars are born, they live, and they die, and if we want to survive, we must learn to outlive our own. It is easy to imagine the Earth as eternal, with the sun rising each morning as it always has, but astronomy reminds us that stars are mortal. Our sun was born about 4.6 billion years ago, and, like all stars, it has a natural lifetime. On the cosmic clock, we are halfway through its story, with roughly another 5 billion years before it swells into a red giant and eventually fades into a white dwarf. Yet for humanity, the deadline is far sooner. In just a billion years or so, the sun's gradual brightening will push Earth into a runaway greenhouse, boiling our oceans and stripping our planet of its habitability. Long before the sun's final flare, Earth will no longer be the lush home it is today, and as we'll see today, there are any number of natural disasters or artificial man-made accidents that might accelerate this timeline. And so the question becomes, what does humanity do about it? Do we try to preserve Earth itself, move it farther from the sun? Do we adapt to a frozen world if our planet drifts alone as a rogue? Do we abandon the cradle and scatter into the stars? Or do we seize the tools of stellar engineering, lifting fuel from our star and even kindling new suns to take its place? Today we'll explore these options, how civilizations might survive the death of their star, and what strategies could keep Earth, or at least humanity, alive when the sun's time is finally done. Ways the sun could die or become inhospitable. When we talk about the sun dying, what we usually mean is a slow brightening and eventual transformation that comes with stellar aging. Our star is about halfway through its 10 billion year main sequence lifetime, quietly turning hydrogen into helium in its core. But this is not a steady process. As helium builds up, the sun's core gets denser and hotter, fusion rates climb, and the sun grows steadily brighter. A billion years from now, it may already be too bright for Earth to sustain oceans and life as we know it. In about 5 billion years, the sun will expand into a red giant, possibly engulfing Earth before it sloughs off its outer layers and shrinks down to a white dwarf. That's the normal stellar script, but some stars have even more chaotic retirements, exploding as novas or sending out deadly bursts of radiation. A nearby supernova or gamma-ray burst could strip away our atmosphere in seconds. A rogue black hole or neutron star wandering too close could perturb the solar system's orbit or even eject Earth entirely into stellar space. Worse, they could enter into a binary state, wreaking havoc on normal orbits and eventually colliding in a titanic explosion or a slow-motion deadly merger. And it doesn't take something so exotic. A near miss with another star or a massive passing body could destabilize planetary orbits, moving Earth inward into a scorched wasteland or flinging outward into the icy dark between stars. We might even imagine artificial misfortunes. If a future humanity masters techniques like Starlifting, moving mass from stars for energy materials, which actually lets you extend a star's life when properly done, but a miscalculation could destabilize the sun prematurely, or perhaps we one day attempt star building or star merging and wind up with a far less habitable neighborhood. Maybe an AI gets loose and doesn't care much about stable lighting and surrounds the sun with solar collectors while altering its spectrum and output, or even disassembling the sun for raw materials. We might be left alone during that, as Earth is one of the worst places to mine for resources in the solar system for space-based use, and have a period of time trying to figure out what to do. So too, we can imagine any number of star-killing weapons that civilization might create, even inside the realms of known science, like a relativistic metallic asteroid impacting the sun, or two colliding at its center. In short, the sun's death is inevitable, but its timetable and the manner of Earth's fate are far from fixed. Nature provides plenty of ways to make our star hostile long before its scheduled retirement, and human ambition may add more to the list. Surviving a frozen Earth. We can imagine scenarios where the sun slowly fades out. We see that in sci-fi like Gene Wolfe's Book of the New Sun or the film Sunshine. Early sci-fi tended to assume the sun would slowly cool off. We didn't really understand how nuclear fusion and stellar mechanics worked, so a dying ember made sense. Instead, the sun will steadily heat up before going red giant, and we actually might survive that by slowly moving the Earth a bit further out or deploying reflective sunshades to cut down the light coming through. Once that phase ends and the sun goes white dwarf, you'd have to move Earth closer again, and now the dying ember scenario is correct. though you could feed the sun new hydrogen in a trickle, carefully to keep it hot. But even if all the fusion in the sun stopped tomorrow, it would take a long time to cool noticeably, and each additional degree of cooling would take longer than the last. Exact numbers are tricky, but if fusion stopped now, it would take a couple million years for it to drop 100 Kelvin. Given that surface temperature is 5,770 Kelvin at the moment, that would be a 1.7% decrease in temperature and a considerably bigger drop in luminosity, about 7%. The habitable zone would contract about 3% too, and we would expect, in a first-order approximation, for Earth's average temperature to drop 5 Celsius or 9 Fahrenheit. That actually might be enough to snowball Earth all on its own, but my hunch is that we would still be naturally habitable. There's a lot we could do to prevent that, such as adding orbital mirrors to give us more sunlight, and either way, that's a very gradual drop, and still requires a very impossible scenario, something causing fusion to simply stop. What could make the Earth cool faster? The most probable near-term scenario would be an ejected black hole passing by our solar system. It could get very close before we notice, especially as the process that ejects black holes from the galaxy tends to result in very high speeds, and would more likely than not pass through without hitting anything at all, or nothing bigger than a small rock. But its gravity would be very real and disruptive. It could flat out eject us, though the more likely scenario is that we get pushed to an orbit further or closer to the Sun. However, even an ejection is likely to be a thing of many years. We would see a white dwarf, neutron star, or regular star a long way off, tens of thousands of years in advance. And I think your strategy there is to send a colony fleet to that stellar body with the intent of surrounding a thin screen of mirrors and magnets to turn its own starlight into a drive system, such as the Shkata thruster, to nudge to the side of our system as much as possible. You can also use the same sort of mega engineering, especially with time on your side, to prepare to correct nudged planetary orbits. In any event, if Earth drifts away from the Sun, whether from natural orbital decay, a stellar near miss, or an outright ejection into interstellar space, the first thing we lose is sunlight. But darkness is not instant death. Most likely we corkscrew out. The escape velocity of the Sun from this far away is 42 kilometers or 26 miles per second. The Earth already moves 30 kilometers per second or 19 miles per second, so you have to get 12 kilometers or 8 miles per second added to Earth's speed to get it out of the system. And add it in the right direction, or you need more. Less than it just enters a new orbit further out. Let's assume it was 30 kilometers or 20-ish miles per second we got added, which is on the high end of what is plausible honestly, though a black hole could do a bit more without being ruinously close to Earth. I could make the case that a 10 solar mass black hole could pass within 1 AU of us, that's the distance to the Sun, without wrecking us completely, maybe even half an AU, and your maximum slingshot at 1 AU should be about 80 miles or 130 kilometers per second, and at half an AU, passing right between us and the Sun, that jumps to 120 miles or 190 kilometers per second. Those are the maximums, and for our case of getting more like 30 kilometers per second, that black hole need not get closer than Uranus or maybe Saturn. It's not just proximity, but relative trajectories during that pass that matter. Earth isn't the only body getting messed with too, and you could end up with weird states like us losing our moon or Earth becoming a moon of Jupiter, or double planeting with Venus or Mars, all out beyond the solar system. But it would take a long time to get there. Even at 30 kilometers per second outward, you're looking at about a month to drift out to 2 AU, double our normal distance and out past Mars. As we gave it a pretty high speed, it hasn't lost much of this hyperbolic trajectory. Indeed, even when we get out to about 10 AU in about 10 months, our speed will only have dropped by about a quarter. We are 10 times further from the Sun at this point, and now receiving just 1% of the sunshine we used to, and that will continue to drop to about 0.5% by the end of that first year. Amusingly, the daytime will still be comfortably bright enough to walk around in, and for a few more years too. Our eyes are logarithmic, so we tend not to realize that your typical bright room inside a house is well under 1% the light outdoors at noon. Cooling will be way faster though. For weeks to months the surface cools steadily and agriculture becomes tenuous long before the ground ice is over. Within months, most open farming would fail, and even in greenhouses it won't last much longer. Precipitation will fall off quickly, and within years oceans will begin sealing over with thick ice. Instantly, this does not mean we get buried in snow. We've only got about an inch of water hanging in the sky, planet-wide at any given time, which would translate to 10 inches of snow, though most of that would still fall as rain in the first few weeks. Nobody's getting buried in ice, and as it cools, there's no more evaporation to make that happen. A lot depends on Earth's actual exit speed and time of year it occurs at, but you probably could get one more harvest before the end, maybe even two in equatorial regions if you're spinning out slower than we proposed. Either way, if we're on a hyperbolic trajectory, even a minimalist one, we will be 3 AU out from the Sun in at most 10 months. Any lower speed is not hyperbolic and just settles us into a new orbit. At 3 AU, you still get enough light to grow plants under glass. Again, this is the best case time scenario. Effectively 2 harvests for the surface is useless for agriculture. So within that first year we'd have to abandon the surface. Surfaces lose heat quickly, but the interiors cool slowly. Earth's core is still hotter than the surface of the Sun billions of years after it formed, thanks to insulation and some radioactive decay. Within a few decades though, the surface will be locked in ice, with even the atmosphere condensing into liquid nitrogen and oxygen and settling as frozen layers. Yet this wouldn't snuff out all life immediately. Deep oceans could stay liquid for millennia, perhaps indefinitely, warmed by geothermal and tidal energy, assuming we can keep the moon. Humans would also have options. Subterranean bunkers, underwater habitats, and fission reactors would sustain enclaves for tens of thousands of years. If by then we've mastered fusion, we could keep those bunkers warm indefinitely and even expand them, especially since fusion makes a continuing space program viable, harvesting fresh deuterium when local stores run low. Without fusion, we'd rely on fission for light and warmth, slowly retreating deeper into the Earth for geothermal support. Well-insulated growing chambers would keep crops alive under artificial light, while miners sought uranium and thorium to keep the lights on. Realistically, it would be impossible currently to bunker all of humanity in time, or build enough reactors in a few decades, but the core itself might offer another option, freezing those who could not be sheltered, a grim lottery of hibernation. While that would stave off utter social chaos is uncertain, but would at least offer the chance of a future thaw. Now, you are not limited to just 1 year to make this happen either. You should have advanced notice of any body. Even a black hole isn't likely to get within a light year of us undetected, and even at the more or less maximum speed of 500 kilometers per second, that's still a 600-year head start. So assume you've got at least a couple of centuries of prep time. And as our astronomy improves, this detection window grows, as do our other technologies for managing the slow-motion apocalypse or building the infrastructure to support us. If Earth were ejected into the void, the planet's geology would continue much as before. Volcanism and tectonics would persist for millions of years, potentially creating habitable pockets near volcanic vents beneath the ice. Civilization might survive in bunker hives, powered by stockpiled nuclear fuels. Just a few kilograms of uranium or thorium could keep a small family's enclave heated and lit for generations, and geothermal would function for many millions of years too, though you need to dig ever deeper and eventually might not be able to handle the pressure of all the material above you. And while it's tempting to imagine humanity instantly dying with the sun's absence, the reality is less sudden. Even with no preparation, we would have months to salvage crops, years to retreat underground, and millennia to build a sustainable Dark Age civilization beneath the frozen crust. Moving the Earth, including if ejected. If Earth can no longer stay where it is, perhaps the answer is simply to move it, either to get away from the dying sun or, if we've been ejected already, to guide us to a new sun. That sounds absurd at first glance. We tend to think of planets as immovable anchors in space, but in truth they're just objects bound by gravity, and with enough time and energy their orbits can be nudged. Over aeons, even a small push adds up. One of the more elegant approaches is orbital migration by way of gravity assist. Just as we send spacecraft slingshotting around planets to save fuel, we could redirect asteroids and comets to fly past Earth in carefully timed encounters. Each pass would impart a tiny tug, stealing or giving angular momentum. Done often enough, this could gradually shift Earth's orbit outward, matching pace with the sun's brightening to keep the planet in the habitable zone. It's like nudging a marble around a bowl by tapping the other marbles against it. Slow, fiddly, but effective given millions of years. At a larger scale, we could build stellar engines, megastructures that use the sun's own light or matter as propulsion. The Shkata thruster is the simplest idea, a colossal mirror that reflects more sunlight in one direction than another, giving the entire star a slow push. Over millions of years, the whole solar system could be towed along, Earth included. More advanced designs would use captured stellar wind and fusion exhaust to literally drive the sun like an engine, repositioning it and its planets on cosmic scales. The benefit here is that you're not just moving Earth, but carrying along the entire familiar neighborhood. But you can use the sun to just move Earth. We don't want to focus a huge beam of light or particles on Earth, it would kill us pretty thoroughly, but large space towers poking over the atmosphere or orbital mirror rays can absorb far more. Of course, there's the brute force option, putting rockets on the planet itself. In principle, we could mount enormous fusion candles on the poles, massive thrust towers burning fuel from the sun or comets to push Earth directly outward, or surround the equator with mass drivers that fling material into space, each recoil pushing the planet a little harder. The engineering is staggering, but the physics is straightforward. Push hard enough and Earth moves. You really could attempt this, though the smarter play would be to put the thrusters on the Moon instead of Earth. You would want two of them, one facing Earth, the other pointing out into space on the far side. At each new moon, when the Moon lies between us and the Sun, you'd fire the outward thruster, nudging the Moon closer to Earth, but also pushing it away from the Sun. Then at the full moon, when it's on the far side of Earth, you'd fire the inward-facing thruster, pushing the Moon back out to its original orbit around Earth, while again giving the outward shove from the Sun. Over many cycles, this keeps the Moon's orbit stable around Earth, but slowly drags both of us outward from the Sun. And if you don't like thrusters, just replace them with something more dramatic, a series of gigantic nuclear blasts. One every couple of weeks, at the new and full moon, one briefly lighting the Moon up like an eclipse, a short dark sun rising, and the other making the full moon briefly brighter. It would take roughly 10 to 33 joules to push Earth out to a roughly Martian orbit, which might be where we'd want to be in a billion years as the sun warms. You would need 240 quadrillion megaton nukes to supply that, and spread over a billion years that's 240 million megatons a year, or 20 million a month. Which is a lot of bombs, though we can build them stupidly big. Fusion benefits from scale. It would be as bright as the sun from Earth for several seconds if we were detonating 10 million megatons of blast every couple weeks. You'd probably spread that out over several hours, though. You'd also reduce this by having it vaporize bits of the Moon off as super hot rocket fuel, or by importing ices from further out in the solar system to blow off instead. We are talking about huge amounts of energy, but spread over a long enough time, it works out to be something like 10 to 20% of the energy Earth gets from the Sun. Ironically, as the star ages and gets brighter, you could reflect much of that new light away and keep the Earth cool while pushing us further out where it's dimmer. But what if the Sun itself destabilizes, or if a passing star or black hole gives us an unplanned shove? A near miss could eject Earth entirely, sending us careening into interstellar space. At that point, all the schemes for controlled migration vanish. Earth would already be a rogue planet, its fate sealed by orbital mechanics. That is not necessarily the end of us. A drifting Earth would resemble the scenarios we've already explored for frozen rogue worlds. The same survival strategies apply: bunkers warmed by fission or fusion, domed habitats lit by artificial suns, deep ocean refuges tapping geothermal heat. Our world would continue as a kind of interstellar arc, carrying us across the void at tens of kilometers per second. In fact, the very kick that ejected us, whether from a passing star or engineered propulsion, could be what grants us a permanent escape from a dying sun. Of course, all these schemes share a common theme: enormous patience. To move a planet or to let gravity itself hand us off to a new destiny requires millions of years of planning and civilization-level continuity. None of this can be achieved in a hurry, and certainly not by a fractured or short-sighted society. It's a project for civilizations that think not in decades, but in geological ages. Still, the thought is empowering. Earth doesn't have to stay chained to a dying star. With foresight and persistence, we could shepherd our world to new orbits, even new suns. And even if the cosmos itself tosses us adrift, that isn't the end. It's merely another road, and humanity has always been good at traveling roads. When we talk about moving the Earth or finding a new sun, what we're really talking about is the power of the human imagination and how far learning can take us. That's why I'm delighted to be working again with Imprint, a learning app that makes understanding the universe easier, faster, and far more engaging than you would expect. Imprint's lessons are short, animated, and beautifully visualized, turning complex ideas in science, technology, and philosophy into stories you can absorb in minutes. As we've often discussed, that's the best way to learn, in part because you can do it anytime you have a few minutes, rather than doom-scrolling through social media or clickbait news. You can explore courses on astronomy, the science of happiness, or even decision-making, because preparing for the distant future starts with understanding ourselves today. Millions of learners already use Imprint to replace passive scrolling with active discovery. Build knowledge one bite-sized lesson at a time. Try Imprint free for 7 days and get 25% off an annual subscription at imprintapp.com/IsaacArthur. Evacuating Earth. Earth outmasses the entirety of humanity by a factor of about 10 trillion to 1, so it takes about 10 trillion times the energy to move. Even for the entire biosphere, all of our biomass is less than a billionth Earth's mass, so if moving the whole planet proves too slow, or fate gives us a deadline, we leave. Not as a panicked stampede, but as a staged migration that turns evacuation into expansion. Start early, build lift, build homes, and decide what and who we're actually saving. We did deep dive this some years back in an episode titled Evacuating Earth, so I'm going to move through this a bit faster, see that episode for details. First, throughput. Evacuations fail at the launch pad, not the destination, especially if the destination is already built up, which is probably the case if you're building spaceships in bulk anyway. We would stand up mass throughput systems, space elevators if materials allow, orbital rings and mass drivers everywhere else. Ideally, you still get as much of your in-space bulk material off the moon or asteroids, but with sufficient launch infrastructure in place, bulk cargo launches, water, soil, steel, seed stock, rises cheaply while habitats are assembled in orbit. A hidden gotcha, heat. Billions of vehicles roaring through the atmosphere and blasting back to orbit would dump lethal thermal loads in the air. Rings and tethers sidestep that bottleneck and are the only sane way to move civilization at scale. Second, places to go. You don't ship 8 billion people to one planet, you build millions of homes. O'Neill cylinders, burnospheres, and free-flying towns let us copy-paste Earth's comforts. 1G, blue skies, seasons on demand, without waiting centuries for terraforming. Once a backbone of habitats exists, the evacuation becomes a fairy schedule. Third, who and what goes first. Triage is ugly unless you start early. Contrary to sci-fi instinct, you don't pack the Ark with Nobel laureates. Refugees need operators, builders, farmers, teachers, medics, and leaders who can stand up a working town on arrival. The reality is that you're not spending much effort on research in the immediate decades that follow. Your geniuses, a couple centuries later, can relearn advanced science from archives fairly quickly, and it shouldn't take you more than a couple generations after recovery to fully restore your research capacity, considering you built it in about that time originally, and without actually having a huge archive of tested science to work off of. Instead, families matter, cohesion matters. You don't stock a lifeboat with solitary geniuses and expect a civilization on the far end. You also don't need their genetics. You could easily store sperm and eggs from the best and brightest if you wanted to, but while IQ has a hereditary aspect, IQ isn't that fixed to a specific parental DNA. That doesn't mean you skip your smart people, and productivity is strongly correlated to IQ, as likely would be survivability in such a weird and precarious period of civilization, but it does mean you're building with preserving civilization in mind, not getting new research and art done. You best preserve civilization by sending relatively intact bits of it, and your tilt is to what is most productive and emotionally stable. The library of everything. Earth isn't just people. The modern miracle is that saving the biosphere is now the easy part. Genomes, seed vaults, soil microbiomes, and embryo banks compress into tiny volumes. A Noah's briefcase can carry blueprints for forests, reefs, and farms. Culture compresses too. Art, law, languages, history, redundantly mirrored across habitats. The real challenge is building self-sustained towns that can use those libraries, not storing them. Cold sleep and digital arcs. If time is short and births are scarce, Chronix turns one ship into a city. Pack people in stasis, wake crews in rolling waves as new habitats spin up. Further out, mind upload tech, if it matures, shrinks a person to data. Storage is trivial, the ethics are not, but as a contingency it multiplies options. Scaling to everyone. At cryodensities, a population-scale Ark can be mass comparable to a modest habitat. We wouldn't freeze everyone at once. Awake crews keep building new homes so the frozen have somewhere to live when they're revived, but once orbital industry hums, the problem shifts from fantasy to logistics. With a robust orbital ring, a determined civilization could plausibly clear the planet over decades rather than centuries. If the clock is truly brutal, shipping billions of chronically preserved people to friendly colony systems is viable. Keeping things frozen in space isn't particularly resource intensive. In an extreme pinch, you do not need full-body cryo. Head-only preservation vastly reduces mass and volume. Assuming capable teams and equipment at the destination to restore people as resources allow, you can probably do this in a more orderly and dignified way than lining everyone up in front of thousands of guillotines in front of a lake-sized vat of liquid nitrogen with their name written on their forehead, but that would work. Realistically, there's a narrow window between full-body capacity and head-only capacity, perhaps just a few decades of industrial growth, and not much before tight but livable quarters for the whole population are feasible on large ships. Prevention versus departure. One last sobering filter. In most disaster scenarios, if you have the lift and time to evacuate billions, you usually have the technology to fix the problem in situ, nudge the asteroid, shade the sun, sterilize the pathogen, or build defensive fleets. Evacuation is for the rare cases you cannot stop, or for the long, slow fade where leaving is simply wiser than fighting entropy at home. Bottom line, evacuation isn't fleeing from the night, it's civilization switching from planet-bound to space-native. Build the launch spine, pre-position habitats, stock the libraries, choose for community and competence, and the rest becomes a queue rather than a panic. When the time comes, Earth won't empty in a day, it will flower, one ring road at a time, until our sky is full of hometowns, and leaving the cradle feels less like doom and more like a commencement. Starlifting, refueling, and making new suns. If leave and move are the emergency doors, tend the fire is the long game. Stars are not sacred, they are engines, and engines can be serviced or even built from scratch. Starlifting is the wrench. By heating or magnetically pumping the photosphere, we can bleed plasma off the sun in controlled streams, harvest the useful metals mixed throughout, and, most importantly, trim stellar mass to dial down luminosity and extend lifespan. Drop the helium ash, keep the hydrogen, and you slow the clock. Keep lifting and remixing, and you can extend a main sequence lifetime essentially as long as you have fuel to add back. You also retrieve more metallic matter from the sun while doing this than if you mined out every planet in the solar system and several times over, so it yields a lot of construction material. The fuel can come from the neighborhood. Gas giants are the easy hydrogen mines. The sun itself is the bank you tap once the plants are spoken for. As you starlift, the stars dim faster than you might expect. A small decrease in mass means big reductions in brightness, so a civilization building out a Dyson swarm actually needs less structure over time, not more. Meanwhile, the lifted metals, oxygen, carbon, iron, etc., are exactly what you need for habitats, ships, and shields. Refueling is the other side of the wrench. If we trickle hydrogen into a degenerate core, or a white dwarf, we get steady fusion, often seen by astronomers as soft X-ray sources. You wouldn't live under that light directly, but a shell or swarm that absorbs X-rays and emits them as visible illumination can power a civilization far beyond what the present sun provides. You can even top up a white dwarf for spans longer than its original main sequence life, carefully to avoid Type 1a supernova lines. Black holes are paradoxically the safest furnaces to feed. An accretion shell turns mass into radiant power with efficiencies fusion can't touch, giving you a tunable, immortal sun, so long as you keep the hopper filled. If the future calls for new stars outright, we can oblige. Star making is logistics. Gather hydrogen and tune helium metallicity to set the spectrum and lifetime you want. Merge brown dwarfs or shepherd superjovians to build a modest sun, or use controlled starbursts and shock fronts to seed clusters where you need them. You can even design custom suns, helium-enriched blue dwarfs that shine sun-like yet live longer, or quiet red dwarfs that sip fuel for trillions of years, or even black hole-powered artificial stars. Then place the habitats at the comfortable distance you choose. Taken together, these options shift the frame from survival to stewardship. We're not passengers praying the fire lasts, we are the fire keepers. We can dim the sun when it grows too bright, refuel a cooling ember, or light entirely new hearths wherever we settle. And when the day finally comes to leave this cradle behind us, we don't abandon a dying light. We depart knowing we learned to tend it, to kindle others, and to carry daylight with us. That's not an ending. It's the craft of a species that plans in aeons and writes its own dawns.